Welcome back, everybody. We we are now continuing on discussing our way of quantifying things about welding. We have talked about voltage in welding. We have talked about the powers associated with welding. We last class we talked about how to put these voltages and powers to good use to to calculate the position rate on welding, and we had examples of how well these numbers work in predicting the numbers we would get from the welding guide from Lincoln and pretty much very all these MIG welding processes, both for steel and aluminum. And these same fundamentals apply to pretty much any other metal, and in addition to other processes such like subarc welding or stick welding. And in each of them, like we would be using the proper electrode extensions and electrode diameters. Now that we talked about how much mass we're getting out of our torch, out of our electrode, let's talk about how that mass goes into a weld. So most of the class today is going to be, well, half the class today. I also want to talk about efficiencies, but it's going to be something very, very simple. That is, if I get so much mass out of the electrode, there is so much mass in my weld. And although the mass balance at this level we're doing it, that is very basic, is simple, people in practice seldom do it. Even in our lab, we have tried to get a right cross section just by trial and error. Of course, that's a terrible thing to do, because if you know how much money comes, how much mass comes out of the electrode, you should know how much goes into your plate. And this test of doing trial and error, that's a waste of time and money. And although the exact numbers in reality, you always want to check with an experiment, ideally, a good engineer would do this one experiment to verify that the calculations were right, not because we're clueless trying to figure out what to do, wasting time of the machine, wasting energy, wasting material, and in addition, having to cut to measure. So let's talk about mass balance. And perhaps the most difficult part of this today will be the notation, because we need to give, if we're going to make calculations, we have to have symbols. And then we need symbols for what is the wire, what is the plate. And here we go. Deposition rate. We're going to distinguish between two types of deposition. The instant deposition rate, that is, as we're welding, what is happening, and then the overall deposition rate. That means from the day you open your shop and you start welding to the moment in which you close shop in the evening, how much have you welded? Those are two different things. Let's start talking about what is instantaneous. So an instant mass balance says, this notation is very similar to the notation we use in the heat transfer class. This dot means per unit time, and M is mass. It says how much mass, right? How many kilograms per second or pounds an hour. And for D, I'm using this for the deposit, right? For what the molten metal that is deposited. And the subscript C, we're using here for consumable. So it says, how much mass have I put in my weld, in my deposit, is the same mass as I have burned from the consumable times a consumable efficiency. So we would agree, nothing is 100%. So if I have so many kilograms or so many pounds of electrode, not all of those are going to go into the weld, right? And of course, I will get into more detail soon, but if I have a stick electrode, the fluxes get chipped off. So right there, I know I'm losing some mass. If I have spatter, I'm losing mass. So I know this efficiency is always going to be less than 100%. But this balance is fairly simple. Now, I suggest to express this amount of mass that that comes from the electrode in two parts. One is the linear mass of the consumable, is how many kilograms per meter of consumable we have, or how many grams per meters of consumable that is typically tabulated in the commercial literature. And this, I'm using V because it's an old note, but this is the velocity of the consumable. This is this is the wire feed speed, right? Wire feed speed, the one we set up in a MatE machine or in a sub-arc machine, flux core, metal core. For the case of metal core, right, the linear mass of the consumable is density times cross-sectional area. And if it is solid wire, we can calculate very easily. And we have this formula that might look like complex, but really this formula all it says is density times cross-sectional area. That's all it is. When we have more complex things such as metal core, we don't know many things, but typically you know how many pounds per or how many ounces per foot of wire are there. All right. Let's talk about overall deposition rate. So overall deposition rate is an average. So it's an average over the whole day. And for example, if we know that we can deposit so many pounds an hour or so many kilograms per minute or kilograms an hour of weld when we're welding, we have to account for the time we are not welding. For example, in the case of stick electrode, we need to stop, change the electrode and go. Sometimes we need to stop, grind, pick an electrode and go again. Sometimes we need to stop and, for example, in the case of sub-arc welding, we need to stop and get the and clean up the slag, right? And this is this number is very shop dependent, very application dependent. I will give you some numbers, but are very ballpark. So whatever number I give you, somebody will say is a horrible number because every shop has different efficiencies, operating efficiencies based on what type of things they do and what type of equipment they use, what type of like industrial engineering arrangements they have to be more efficient. Okay. So about the operating factor, I'm going to discuss this more later, but I'm already giving you some ballpark numbers. How in stick welding, you would be welding 15 to 40% of the time. In MIG is higher, and flux core is higher because you don't need to stop and change the electrode. That difference alone, not having to stop and change the electrode, that difference alone is the reason we're having this class, because people have been still rely very heavily on stick electrode in this province. And even 20 years ago, people realized this has short legs. And people started to discuss how about moving to flux core. But it's quite difficult when all your welders know flux core, all your procedures, all your welders know stick welding, all your procedures are for stick welding, or all the quality assessment is for stick welding. And one of the efforts this province did in trying to move away from stick is creating this welding program we are having now. Now, we're going way beyond changing a stick to flux core. Of course, we support that and we do that and we help on that. But by having engineers that know as much as you guys are gonna know, then you're gonna be in a situation not only of moving out of a stick to flux core, but also know when we should and when we shouldn't, and how much we should in some cases, and what other alternatives are other than flux core. Okay, let's talk about the cross-section of the deposit. So this is the amount of mass in our deposit, in the cross-section of our bead. right? We're filling up a groove preparation. And this is just standard mass conservation. This is the density of the material in the deposit, for example, the density of steel in the deposit, times the cross-sectional area of the deposit, and I'm going to get into this cross-sectional area in detail in the next slide, times the travel speed, the welding travel speed, right? So this is how much mass is in the deposit. And for the consumable, we also talked about how the amount of consumable we burn is this linear density of the consumable times the wire feed speed. Okay, and we also knew that these two, how much is in the deposit and how much we are burning, is related through the consumable efficiency. So if we put these three equations together, right, which are very, very basic, it tells us as a result that we can calculate the area of the deposit. And the area of the deposit is given by the linear mass of our electrode, the wire feed speed, essentially how much electrode we're putting, and we divide it by the travel speed, and we divide by the density of the deposit. And of course, we have this efficiency, this consumable efficiency here. What matters here is we have just related what consumable we have with what wire feed speed we have and what travel speed we have. And now that gives us what cross-sectional area our deposit is going to happen. We don't need to measure it. This is very accurate. And of course, we know very well our wire feed speed. We know very well our travel speed. The densities are very well tabulated, and the linear density of the electrode is very well tabulated in the consumables information. The consumable efficiency we might not know exactly, but it has a very narrow range of variation. And I'm giving you in these slides a good list of what these values can be. So this cross-sectional area of the deposit, we can predict quite well. If instead of predicting it, we're just welding and cutting just to see what happens, that's kind of sad, right? In the case of solid wires, the efficiency of the consumable is the metal efficiency. We have no fluxes that we're losing, so we might lose metal by spatter, right? That's the efficiency of the metal. So it's relatively simple, and we can express this cross-sectional area of the weld with this formula. That again, I don't want you to memorize this formula, and the quiz will be with all your notes. It's just to show you how we can get into the very concrete for the case of MatE with solid wire, starting from this mass balance. I promise you to discuss more what the cross section, what I'm talking about by a cross section. For example, let's say this open square butt joint. So we have a gap, let's call it D, and the thickness of the plate is H. So what we need to fill up with our electrodes is this area here, right? Easy is a rectangle, this the root opening times thickness of the plate. This calculation, so simple here, is the same calculation we have here. Now, what is the difference? This calculation here relates only to the geometry of the joint. This other calculation here relates to the process, to my wire feed speed, to my travel speed, to what consumable I'm using, to what efficiencies I have, and losses in spatter or whatnot. If putting these two together, this one from the drawing and the other one about the procedure, then I can start designing the procedure from scratch. this joint is very easy. How about this one that looks more realistic? And in this case, what we need to fill in is all this area here. Something very interesting. After I weld, if I look at the cross section, all this part is going to be molten too. So when I look at the weld, it's going to be look bigger than just what I marked here as 1, 2, and 3. However, that base metal that was molten, I didn't put it, was already there, and it remelted as I was welding. I don't need to account for that material for the mass balance. So all we need to account for to do a mass balance is the joint preparation, which we know from the drawings. So we're in a great shape because we have close to nothing empirical here, all calculated with the basic algebra of high school. So what would we have here? If we have a joint like this, I would split it, and let's say that the root is flush to save ourselves some headaches. I can split this into 4 areas, 4 types of areas, right? One area would be like a rectangle. The other area would be a triangle. We have 2 of those, but they are the same, right? So we have a rectangle, we have these triangles here, and then we have these, the cap pass. And let's see, let's start with number 2, that is the easiest of all. This rectangle that I put some imaginary lines here is base times height, right? Here, this is the same we knew before. These triangles we have here, this is basic trig. So it's base times height over 2, right? And where do I have it? Here. So if this is the land at the root, and we have h is the whole thickness of the plate, so I do thickness of the plate minus the land, and would give us the length of this. That would give us the length of this of this side of the triangle, right? Now, the height of this triangle would be this same length, right? Is h minus hl, right? Times the tangent of this angle. And we know from the drawing, because this is half the groove angle. This is the bevel angle, right? So we have this, if the bevel, the groove angle is alpha, this is alpha over 2. That's the bevel. The tangent of that times this side gives us this other side here. So we have h minus hl one side, h minus hl tan is the other side. So that's why we have this multiplied twice with square. That's why the tangent appears, and because it's a triangle, it's a 1/2. So we have just calculated the area of this bevel here. So we see we have in the total area, we have this area that corresponds to the rectangle, 2 times the area of the triangles, because we have 2 triangles. And let's talk about the top here. This is super interesting. And that depends, the cap pass depends on the welder, depends on so many things. Some people say, hey, I'm going to consider this is a segment of a circle. Yeah, why not? It's reasonable. And if you do that, you can have a formula that says, well, based on this, on the height of the reinforcement, and based on the width of my reinforcement, I can assume it's a sector of a circle and do a calculation. That calculation is not exact, because really it's not a sector of a circle. And also it's a very complex calculation. Let me tell you something we have been doing in the lab, and we have measured, and this works awesome. And we have tested it. much simpler math. And in the end, I found that in the Lincoln Procedure Handbook, way at the end, they suggest to do exactly the same. If instead of assuming that this is like a sector of a circle, you assume it's a sector of a parabola, which is not exact either. Just the same way a sector of a circle is not exact. But more or less, a parabola would be like flat here at the top and would be joining these at some sort of a shallow angle at the toes. If we assume this is a parabola, then it's very easy to calculate this area. And you know what it is? The area of the cap passes would be 2/3 the width times the height. Isn't this awesome? In triangles is 1/2 base times height. Here is 2/3 of the width, the base times the height. This is pretty cool. And it's exact for a parabola. And when the reinforcement is shallow, as is most often the case for welding or for laser cladding, for example, this formula, which we have tested very much for laser cladding, works really, really well. So now you know how to calculate a rectangle and the triangles because you passed high school. And I'm telling you a really handy way of calculating reinforcements that is also quite accurate. Now, you know how to calculate the cross-sectional area to be filled in pretty much any joint prep. And you know also how to relate that cross-sectional area to process parameters like wire feed speed, travel speed, electrode diameter. Now, we can make predictions without testing, and this is very accurate. There is no physics here, it's only geometry. So let me give you an example, and this example, in retrospect, I don't like it so much. It's all real numbers, but I'm asking you to calculate here the wire feed speed in subarc welding. The reason I don't like this example so much is because you seldom, wire feed speed comes together with current, and you seldom leave that for the end. You typically start by saying what current you want. And if you know what current you want, because of deposition rate, you would know what wire feed speed you would want. That said, and just for the sake of the exercise, let's use this math we have discussed to predict a wire feed speed in subarc welding. So here we have this is a fillet weld, and I'm giving here some number for the convexity of the weld. Sometimes it's flat, sometimes it's concave. So we want to do a single pass that is that has this amount of concavity. What should be our wire feed speed? We have here the travel speed, right? And the electrode diameter. Okay, so here we have the formulas we had discussed. We have cross-sectional area of the weld, which is this, everything that is in gray, times travel velocity, right? Which it was part of the statement. And we have the cross-sectional area of the wire, that because it's circular cross-section is very easy. You see is the wire feed speed, that is the unknown. And here we have the efficiency of the consumable. And in subarc welding, the consumable efficiency is fairly high because most of the spatter is caught by the slag and falls back into the weld. It's not the same in the case of flux core because the spatter flies away and goes away. It doesn't have a wall of flux to catch the spatter and come down. And this, which is in your notes, you can follow this. You can follow this calculation, do the numbers yourself, and it's going to give you the wire feed speed for this problem. This is extremely powerful. These type of parameters are typically decided by tinkering. The problem with tinkering with welding is that it's easy to tinker But there are so many variables that this easy job is a very tedious job because so many things can be changed. Old people have a pretty good feeling for what to change and what's going to happen. Younger people tend to change whatever and get whatever results. It's not going to be your case. You should be able to anticipate things. Look at this. None of this requires advanced math. It's just like very basic things that if you ever have a job in a shop, you might as well put these formulas in Excel and go to town. So here is in this last slide about mass conservation, I'm putting some things together. Do you remember we mentioned on Tuesday that in the end we can say that the deposition rate relates to current, right? And we had a number when we wrote this equation for deposition rate. We said this is pretty much constant. This other number here is not exactly constant, but when the current was too high, we would change the wire diameter. So in the end, all across the wire diameters, this term is more or less constant. So this is constant, this is more or less constant. This is so small that we don't need to worry. And we came to a prediction that in MIG, the deposition rate is more or less 2.7 pounds an hour every 100 amps, right? We're using these imperial units because we often use that in the province. We said this on Tuesday. All right, now, if I have this 2.7 pounds an hour per 100 pounds here for the deposition rate, and I use these formulas we have just discussed relating deposition rate and travel speed, right? We discussed today. And now I combine this with our definition of heat input that combines deposition, travel speed and current, right? This is a definition of heat. This is the definition of heat input. So I have here something that relates travel speed to current. Here I have something that relates current to deposition rate. And now in this one, I have something that relates deposition rate to travel speed. I put all these together, and you can do. And if we plug in the standard numbers for meg of steel, and is the density of steel, this 2.7 pounds an hour every 100 amps, and we ballpark the consumable efficiency as 1. All this together, it says that the heat input of one pass of a weld, if I have one pass, the heat input of that one pass is more or less 0.6 kilojoules per centimeter. That is a unit we typically use here, per times the cross-section of the weld. This is very powerful. Some of you might be distracted by the math and the symbols, but you know what this means? This means if I kind of cross-section of a weld and I look at the weld, I can tell you the heat input. Isn't this awesome? And I can tell you the heat input without knowing the voltage, without knowing the amps, without knowing anything. I just look at the cross-section and I can say, if the cross-section say is 10 square millimeters for each pass, if each pass is 10 square millimeters, then using this, I do 10 square millimeters times this 0.6 kilojoules, and I would get 6 kilojoules per centimeter. You know what? Yeah, that's about right. And if you have a bigger pass, like a hot pass, right? Hot pass is bigger. What does it mean? Bigger heat input. And I use this formula and I would get it, right? So if I ever give you a cross-section of a weld and tell you nothing about it other than it's a weld made out of steel, Oh, by the way, I forgot to tell you, although I'm using MIG as an example, this number is fairly, you can redo this for sub-arc welding or for stick welding, and the number always comes more or less the same. Is it exact? No. Is it a lot better than ignorance? Yeah. It's actually somewhat accurate? Yes. So you can see a cross-section of a weld, and I just walked you through every step and justify the things, starting at the anode fault voltage and cathode fault voltage, such that you can see a cross-section of a weld and say, this weld had so many kilojoules per inch in heat input. And then you would start to know, okay, is this a high heat input or low heat input based on your experience? On Tuesday, we'll start discussing, if you have the heat input, can you calculate cooling rate, T85? Can you speculate about the size of the heat affected zone? And all those things start to come out. Very, very interesting. Okay. Something, so this is a practical number. Any questions about the position and mass balance in welding? I believe this material is quite dense, especially that the concepts that we use in words are easy to understand the concept, but when we put them in a formula, we have to give them a name, and then we have to remember the notation, right? That's tedious, and that's sometimes prone to confusion and little mistakes. The good news is you can predict things. The bad news is that as you review this material, you might need to sit down and go over the problems of previous years or this problem we just discussed, and see how you put these formulas to good use. If you just listen to me, it's not likely that you can do it. You need to sit down and do it on your own. Very powerful, very powerful. Okay. What I would like to do is to switch topics to talk about efficiencies in welding. So I'm going to change the set of slides. Okay.